நீராறும் கடலொடுத்து நிலமடைந்த கெழிலொழுகும் சீராறும் வதனமென திகழ்வரத கண்டமிதில் தெக்கணமும் அது சிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை நுதலும் தரிதனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிளமை திறம் வியந்து செயல் மறந்து வாழ்த்துதுமே வாழ்த்துதுமே வாழ்த்துதுமே. Thank you. Thank you so much. Now for lighting the traditional lamp, I request upon Professor Manu Santanam, Mr. Rajesh Ladhar, Engineer Muralidharan, Mr. Senan Shah and Mr. Siddhappa to come onto the stage, please. Thank you, dignitaries. Now I request upon Dr. Kannan Rajkumar, Secretary, ICI Chennai Center, to formally welcome the gathering, please.
Good evening to one and all. It's a privilege to quote the welcome address for today's August gathering. First and foremost, it's my privilege to welcome our Professor Manu Santanam from IIT Madras, who has worked extensively on high performance concrete and UHPC for the past 2 decades, and he has applied in many challenging projects. Welcome you, sir. I would like to welcome Engineer Rajesh Kelarhat, Managing Director, Structural Engineering, Concept Designs, and Engineer Siddhappa Asbi and Senan Shah from kvalitet Resources Mumbai. I also like to welcome all the dignitaries from Kvalitet for their active participation in today's program. And I would like to welcome Ravi Shankar and Molidharan sir, Chairman, ICA Chennai Center, for bringing this program to Chennai and introducing the performance of Silica Fume High Performance Concrete for all the participants. I would like to welcome all the participants in the busy schedule to attend the program. I think so this program will be a mind-blowing session for all the participants. Thank you. And one more thing, I would like to welcome our treasurer, Vasigi, for their active participation. Thank you, ma'am.
Thank you for the formal welcome, sir. So it's our privilege now to introduce and felicitate our chief guest, Professor Manu Santhanam. So Professor Manu Santhanam is a professor in the Building Technology and Construction Management Division, Department of Civil Engineering, and also Associate Dean of Industrial Consultancy and Sponsored Research, ICSR, IIT Madras. He is also active in various professional associations such as ACI, ICI, and RILEM, and has been distinguished as a RILEM Fellow in 2019. He is also a member of editorial board in leading international journal on construction material such as Advances in Cement Research, ASCE Journal of Materials and Civil Engineering, Journal of Sustainable Cement-Based Materials, and Journal of Cement and Concrete Composites. Actually, sir's profile is too big, and so considering the time, I'm just shortening it. I request upon Engineer Muralidharan and Mr. Senan Shah to felicitate Professor Manu Santhanam, please. So time to hear from Professor Manu. Over to you, sir.
Very good evening to all of you. Indeed a pleasure to come and interact with you on this important subject on the use of silica fume and concrete. So I thank Murli and the ICA team for giving this opportunity. I hope that it will set the tone for the discussions that will happen later, because you have a practicing consultant who's going to talk about how concrete durability can also be one of the aspects that can be specified by consultants. I think that's very important. Many consultants only think about strength, but today you'll see an example of how concrete durability can also be prescribed. Something I've been saying in several of my lectures previously, but I'm happy to finally meet people who are actually doing that. And then of course you'll hear from Mr. Hashbi, who's been involved with silica fume for a very long time. So I'm sure that he has a lot more data to show you. So as a professor, probably it's my duty to bring in some academic interest into this entire subject. So I'll talk primarily from the point of view of what silica fume actually does in a cementitious system. So just to take you through a background of what happens in cement hydration, we all know very well that cement is a material that reacts slowly with water, sets and then hardens. When it hardens, what it does, the reaction products of cement basically start filling up the space around, which was filled by water earlier. So as more and more hydration happens, of course this won't work. In the screen, let's work. It's an LCD, so no problem. So when hydration actually happens, the space between the particles starts getting filled up by hydration products. And with more and more hydration, you get complete filling of space and reduction in porosity and permeability. In concrete, the scenario is a little bit different as compared to paste, because in concrete, you have cement paste mixed with aggregate. So close to the aggregate, you have a zone which we commonly like to call as interfacial transition zone, where whatever properties of concrete we don't understand, we generally tend to blame on that zone, interfacial transition zone. It's a bonding zone between paste and aggregate. But it so turns out that there is indeed a difference in the appearance of the zone as compared to the remaining part of the paste. So generally in concrete, if you notice near the aggregate, there'll be more porosity, there'll be more calcium hydroxide, and there won't be as much of calcium silicate hydrate, which is the primary binding material that is formed when cement reacts with water. So as a result, we have a situation where there is an inefficient packing near the aggregate. So whenever there's loading of this concrete, the load obviously will concentrate around the stiffer regions. Aggregate being stiffer than the paste will take more load, and the zone around the aggregate will have a slightly higher extent of stress, because of which cracking in the interfacial transition zone begins without much loading itself. It begins at a very low level of load, and that cracking also is further worsened because of the fact that there's more porosity available in the ITZ. So the packing of the products that are there in the ITZ is not as efficient, and secondly, pores are not filled up properly. So because of this, we generally tend to use what we call as mineral admixtures. Okay, any mineral admixture like fly ash or slag or silica fume will do a good job of trying to fill up the space around the aggregate and densifying the interfacial transition zone. If you have tested concrete, you'll know that when you fail the concrete, the cracks go around the aggregate for most normal grade concretes, right? Unless you go for high strength concrete where the cracks go right through the aggregate. Normal grade concrete, the cracks go around. So to strengthen the interface and to ensure that you get a stronger concrete, you can densify the interfacial zone. So as you become stronger and stronger, the cracks will tend to pass right through the aggregate. So what we are doing here with mineral admixtures, which give you reactive silica, is that we convert calcium hydroxide, which is there in abundance in the interfacial zone, into CSH. Calcium silicate hydrate is the primary binding material, and it fills up the space much more efficiently. So ultimately, concrete is a solid. The more space that is filled up by the solid, the better the strength, the better the durability. That's it. That's the basic science of concrete. So what we're trying to do is converting phases that don't fill up efficiently into phases that fill up efficiently, because of which you get much lower porosity, much lower permeability. And that's what we want for more durable concrete. So I can change with this. Sure. So today everybody talks about sustainability, but we have to look at several different aspects when we talk about sustainability, right? It cannot be just economically viable or just environmentally good, okay, or just socially good. It has to satisfy all three causes if any technology has to be sustainable. Mineral admixtures help us achieve all of these three, what we call as triple bottom line of sustainability. Environmentally, of course, we are reducing cement usage in concrete. And when we do that, we are automatically contributing less CO2 to the environment, because cement manufacture is responsible for nearly 6 to 8% of CO2 emissions. Construction itself is about 20%, but you can imagine 6 to 8% is just coming from cement manufacture. So if you can cut down the extent of cement and concrete, you're already doing positive for the environment. Second is, many of the mineral admixtures are byproducts, which would otherwise go as waste or get dumped, right? We are finding a useful resource from a byproduct, and that's again an environmentally conscious decision. In terms of your social aspect, when we make concrete with mineral admixtures, we tend to make it in such a way that it has lesser tendency to crack, and it generally performs better in the long run, thus giving a better impact socially. Concrete that does not fail is obviously concrete that is good for the society. And economically also, if you look at the long-term performance, use of these materials is going to give you an improved benefit to cost ratio. So as a result, you ultimately end up with a concrete that is more economically viable, but you need to consider the long term. This L1 business of looking at material cost today, that mentality has to go from our minds. We need to start looking at life cycle costing. And that's when we can really understand the importance of all of these supplementary materials better. So what happens in these materials? Obviously, as I said, we have calcium hydroxide from the cement hydration. Your materials that you're using as mineral additives give reactive silica. So when you have silica and calcium hydroxide, it combines to make calcium silicate hydrate, right? Additionally, of course, you have the role of these finely divided mineral additives also as filler. Physically also, they are filling up the space. If you really think about it, all of the cement that you put in the concrete does not react with water. If you're putting 450 kilograms of cement in your concrete, it's only about 250 that's actually reacting. The remaining 200 is simply sitting there as filler. Why do we want to waste money on something that does not react? Of course, in the long term, with continuous curing, some of it will also react. But even if you take like this structure, maybe I think at least 20, 25 years old, take a sample of concrete from inside, you'll find that a lot of the cement is still unreacted. But it is doing a job of a filler. So can we replace this filler, which is expensive, by something that is a byproduct? That's the idea of using mineral additives. And that's where we are really getting an optimized advantage. So in most of your cementitious materials, people tend to look at the composition using what we call as a ternary diagram. So here you have one end which is calcium oxide, the other end which is silicon dioxide, and one vertex is aluminum oxide. So when you look at the composition of all your cementing materials, it can be quite nicely represented in this ternary diagram. So cement we know is calcium rich, so it is at the bottom left corner, close to the bottom left. Of course, exactly at the edge you have portlandite or calcium hydroxide, which is exactly at that vertex because that's calcium oxide is 100% portlandite. On the top you have silica fume, where mostly you have only silica. You don't really have too much of alumina or calcium present, mostly silica. If you look at the other mineral additives, fly ash, calcine clays, slag, etc., these are in different locations within this triangle. Now, what is the importance of looking at it in this way is that based on the initial composition, we can have a general idea about what can form when you replace cement with any of these additives. So, for instance, when you're replacing cement with silica fume, what you can actually end up forming is only CSH. You can't form anything else typically because silica fume does not have any alumina in it. If you go to slag, which has got calcium, it's got alumina, it's got silica, all of those things are there, you'll start forming phases that are towards the center, like your CASH. Nice name, cash, but it's calcium aluminum silicate hydrate, right? You can also form some crystalline phases like stratlingite. When you're going towards calcine clay, which is aluminosilicate, that has to then combine with your calcium to again form your products like CaSH and stratlingite. Fly ash will also be somewhere there. So based on these compositional diagram, you can have a brief approximate idea about where you are with respect to what you can get. Now with silica fume, we are pretty much sure that when we add silica fume, which is reactive silica, it will combine with calcium hydroxide and give you CSH. Now the CSH that you get from that reaction is not exactly the same as the CSH that you get from the cement reaction. Both will have different attributes. That's okay. What we need is a material that fills up space, and that's what we get. So the binders are of different types. One is obviously your cement or hydraulic cement. Anybody remember why we call cement as hydraulic? Why do we call it as hydraulic cement? No, all of these need water. All of these systems need water, without which there is no reaction, right? But cement, ordinary Portland cement, which is rich in calcium oxide, can react with water and set and harden even in wet conditions. Even underwater, cement will react with water and set and harden. That's why it's hydraulic cement. Slag possesses something similar. Slag is called a latent hydraulic material, where calcium content is not high enough for it to be reactive on its own. It needs some activation. And that activation, you may have heard about, some people call it geopolymer, but alkali activation is what is being done there. We add alkalis to activate the slag. So we call it AAS, or alkali activated slag, sometimes wrongly referred to as geopolymer, because that's not what's happening there. What is happening is slag hydration. So slag can hydrate, it can react with water, but it needs some push or some kick because no calcium is there, not enough calcium is there. But when we look at pozzolanic materials, there is no calcium, or almost zero calcium. Okay? So silica fume, fly ash, calcined clay or metakaolin, they are all belonging to the group of pozzolanic materials, which are silica and alumina in abundance, but not much calcium. So there you need to provide calcium for the reaction to happen. Your calcium is coming from calcium hydroxide, from the cement. Cement provides the calcium hydroxide. That's why the combination works very well. When you combine cement, partially replace it with any of these materials, it works well to improve your microstructure. So again, just to explain about pozzolanic reaction, you have your calcium hydroxide from the cement reacting with silica or even alumina, because calcined clay will also have reactive alumina, right? And it will end up producing, of course, water is an important ingredient. Without water, there is no reaction, right? And then you get your mixture of calcium silicate and calcium aluminate hydrates, which is sometimes also given the name as CASH, C-A-S-H, calcium aluminosilicate hydrate. This reaction obviously consumes lime, calcium hydroxide. It refines porosity, as I said earlier. CSH fills up pore spaces more efficiently than calcium hydroxide, right? So it fills up pore spaces, obviously that will lead to better durability, right? It's generally a slow reaction when you consider materials like fly ash or slag. Okay, slag is not really pozzolanic, so this reaction is not true for slag, but for fly ash or for some grades of calcined clay, this reaction is slow. So when the reaction is slow, it will lower the heat of hydration. But for high purity metakaolin and for silica fume, that is not necessarily true. This reaction will be fast also because the silica is present in very fine form, so extremely reactive silica is present. And generally when you have alkali or gypsum in the system, like sodium potassium oxide, which is there in your cement, right? And gypsum also is there in the cement, this reaction gets accelerated, so speeded up. This reaction happens faster. You may have heard of technologies like FALG, right? Fly ash, lime, gypsum. There again you are making use of the pozzolanic reaction, fly ash and lime, and accelerating it with the help of gypsum. So there are people in Andhra who have worked on FALG and have been propagating its use for bricks. It's a nice material to use for manufacturing bricks. One thing we need to understand is these different mineral admixtures will have different rates at which they are providing the necessary property, right? So if we look at highly reactive materials like rice husk ash, when you burn rice husk in controlled conditions, it gives you a very high purity silica also, right? And silica fume, again, very high purity silica. So both of these, at one day itself, they'll be matching the performance you expect with cement. That means there is no slowdown in the rate of hydration. But here we are sure about the kind of replacement we are doing. It's restricted to about 10%. We'll talk about why that happens and why you can't put much more than that. In type C fly ash, which is the one which we get from Neyveli, for instance, it will take about 7 days for the mix with the fly ash to reach the strength equal to that of cement. Now here I'm talking about just replacing OPC with these materials. I'm not redesigning the concrete. Okay, I'm just replacing OPC. Let's say I had 300 kilograms OPC. I'm saying 210 kilograms OPC and 90 kilograms of type C fly ash, like that. It's just a simple replacement. So here, at about 20 to 30% replacement, sorry, my throat is bad. That'll help. Thank you. So at about 20-30% replacement, it will take about 7 days. So that's why we need to cure pozzolanic concretes for longer time. Type F fly ash will take a bit longer because it's not as reactive, it doesn't have calcium. So it takes about 14 to 28 days to reach equivalent strength that of cement. Sorry. GGBFS, 3 to 7 days. Again, depends on the extent, but typically we use a high replacement level of GGBFS, around 50% is what is used in concrete. So, silica fume, the physical properties are quite different from that of cement. Oh, maybe I skipped a slide. Okay. Now, silica fume is typically available in 3 forms. You can get it as it is produced or as collected. You can get it as a slurry or as a densified form. But slurry form I don't think is available in India. It's in the US and some European countries you can get the slurry form. But what we get most often is the densified form of silica fume. I'll show you why we have to densify it to get a density which is around 500 to 700 kilograms per cubic meter. I may be off by some extent. Maybe the lecture by Mr. Hasbi will have the correct numbers. But particle specific gravity of silica fume is about 2.2. Cement, you all know, is about 3.15. So you're replacing cement with a finer material with lower specific gravity, right? So you expect the volume of your paste to go up. You're replacing a denser material by the lighter material. So if you're doing a mass replacement, your volume of paste will go up. Okay? That you have to be sure about when you do the mix design. The surface area, that means if you take individual particle and measure the overall surface area, it is of that order. Cement, you have done Blaine's test, right? Typically, what do we get in Blaine's test? 300 square meters per kilogram or 3000 centimeters square per gram. So compare 300 to 20,000. So here we can't even use Blaine. Silica fume, you can't use a Blaine apparatus because air will not be permeable. Air will not go through the silica fume at all. I mean, silica fume particle bed, you can't really do a Blaine's test. So we use a technique called BET to establish surface area. So you can imagine such a high surface area. That's because of the very small particle size. Less than 1 micron is a general number, but average size will be around 0.3 to 0.5 micron. So cement particles average size is 15 to 20 microns. Here we talk about 0.5 microns. So you can clearly see the distinction in the fineness of the material that we are dealing with. Okay? So as the bulk powder is extremely light and the particles are extremely fine, it tends to fly around too much and it cannot be packaged efficiently. So if you take a regular bag of cement, 50 kg bag, if you try to pack silica fume in that same bag, you may hardly get 5-6 kgs if you take the bulk powder. So that's why to make it easy to handle and transport, we need to densify it. So dry densified silica fume is what is typically available in the industry. And here compaction by pressure is done so that the grains get flocculated. They start forming condensed particles, right? So when you use that in concrete, you obviously need to have efficient dispersion provided by superplasticizer and good mixing with the aggregate to break down the particles to completely remove or distribute the fine particles of silica fume. That's what you want ultimately. As a slurry, there are obviously problems because 50% is water. So imagine storage space. For every 1 kilogram of silica fume, you need to provide storage space for 2 kilograms of material. And again, compensating the water in the mix design, it's a very complicated process. Although, as a slurry, the mixing of silica fume is very easy. But then it has its problems of handling and storage. Just to show you pictures, I'm sure that you'll see better pictures. You can see the bulk powder just flies around. When it's densified, it's almost like cement. Okay? As a slurry, obviously it's a liquid, so it can be used quite easily, quite efficiently. Just to show you a comparison of particle sizes, you can see silica fume sizes are much smaller as compared to cement particle sizes. As I said, 0.3 to 0.5 micron versus 15 to 20 microns. Okay? So because of this, the effects on fresh concrete that can be expected is that you can increase the water demand of concrete. Silica fume should not be used without super plasticizer. I have put a footnote there with a star. Any concrete should not be made without water reducer or super plasticizer. I always talk about this in every forum. If you are making concrete without chemical admixture, you will be spending too much cement to make simple grades of concrete like M20, M25. You can optimize your mix, use less cement to produce the same grade of concrete if you use a super plasticizer. So any concrete today which does not use water reducer or super plasticizer is not sustainable in my opinion, because we're using too much cement to get the workability. Because water cement ratio is fixed, so you increase the cement to get the water to get the workability. But here with the super plasticizer you don't have to do that. So that is true of any concrete. You have to use water reducer or super plasticizer to see efficiency happening in concrete. But silica fume concrete goes without saying, because of the fine particle size and the expected increase in water demand, it should not be used without super plasticizer. Second thing, which many sites are not handling well, is the fact that you need to prolong your mixing with silica fume. Right? Silica fume, as I said, is in condensed form. This has to be broken down and efficiently dispersed by the super plasticizer. How do you break it down? By mixing. The aggregates will tend to break these particles, and the super plasticizer will efficiently deflocculate the particles. So you don't mix well enough, you're not going to be achieving the result that you want, because you want that fineness. That's the reason you're putting it in there. You want that 0.3 to 0.5 fineness to really fill up the spaces very efficiently. That's when it will work very well. And for getting the reactivity. Mix can become sticky and cohesive, so you have to design your slump carefully, because again, any fine material will do that, right? Stickiness will increase. But more important, you need to understand, whenever you're using not just silica fume, any mineral admixture as a replacement of cement, you can expect that if you don't pay attention to the concrete in the early stages, plastic shrinkage problem will definitely happen. Okay? Any concrete with mineral admixture, not just with silica fume. You take fly ash, slag, anything. Because most of these materials are finer than cement. Secondly, as I said earlier, because you're replacing a denser material with lighter, the paste volume is going up. You have more paste in your system, right? So when you have more paste, more shrinkage. Here also, in the early stages, you need to ensure that you protect your concrete from drying in the early stages, especially when you're making some slabs, which have very high surface area, right? So protection of the concrete is important. Simple floating of the concrete when the cracks appear in the beginning, especially true with flowable concrete like SCC. SCC is being used everywhere now. So with SCC especially, you need to be extremely careful about doing floating in the beginning to ensure that plastic shrinkage cracks do not form. Now, hardened concrete, of course, if you've done your concreting well, like all mineral additives, silica fume obviously will give you an additional kick because of its extremely high fineness and its high reactivity. So you get pore size refinement and reduction in permeability, and that's what is the basis of putting silica fume for all your high performance concrete. For high performance concrete, you have to go with silica fume. You get better resistance to chemical attack, improved resistance to chloride-induced corrosion. Silica fume definitely helps in all of these environments. Generally, strength also increases. For a simple replacement of cement, strength will also increase by 7 days, 14 days. One day you may not see that much of an increase, depends on the mix design, but you will definitely see an increase in strength. And the modulus. Your concrete will become stiffer with the increase in strength. In alkali silica reactivity, silica fume can really do very well. But of course, that's also true of all mineral admixtures. Whenever your aggregate is not of good quality, if it's reactive, all of mineral admixtures will help in reducing the extent of expansion. Carbonation resistance. This is where many other mineral admixtures like fly ash or slag, because of the amount that we use, they are generally performing poorer. But silica fume concrete, at least the data that we have seen, seems to have similar carbonation performance. But of course, silica fume is used only generally in high-grade concretes. So when you do that, you expect carbonation to be low in any case. So again, fire performance, of course, we learned this from the accident in the Channel Tunnel between England and France, that fire performance of silica fume linings, concrete high performance linings was not good because it's very dense. When fire transforms the water to steam, the steam does not have a way to come out of the concrete. So spalling can happen. So people have recommended that polypropylene fibers be used whenever fire hazard is there, because when fire happens, the polypropylene fibers will also melt and create the pore spaces through which the water can come out. So with tunnel linings done with silica fume concrete, if fire hazard is a problem, for instance, if it's a roadway tunnel, then maybe one should look at possibility of also using some polypropylene fibers. So when to use silica fume? Okay. Since I'm not giving a marketing presentation, I would say there are some criteria you should apply when you use silica fume. One is, it should be used for high strength concrete applications. It's usually desirable in a ternary blended form with another supplementary material, like cement plus fly ash plus silica fume, or cement plus slag plus silica fume, like that. Okay. For providing good durability characteristics, in many of the specifications today, durability is being specified, especially rapid chloride penetration test. In silica fume concrete, you get excellent results in these environments. Now, very important to understand, silica fume should be used when high quality batching and mixing facilities are available. Make sure that we can do a good job of batching and mixing. Otherwise, mixing these special ingredients in concrete, you are going to be resulting in more worries for yourself if you don't have the right quality of batching and mixing facilities. It's not for general purpose use. Silica fume is not intended for your day-to-day concretes, 20 to 30 MPa. No point in putting silica fume in such concretes. Only intended for high performance, when you need that high strength and durability. And never use without super plasticizer. Very important to understand. Okay? Just to give you some indications of higher grades of concrete, the typical water binder ratios. Of course, this is with Chennai aggregate, because it's not the same when you go to other parts of the country. You may have to alter the designs a bit to get the same strengths. Chennai, we are blessed with excellent aggregate, because of which we can design concretes with generally lower binder contents and moderately higher water binder ratios than we do elsewhere. So, of course, you'll have this presentation. You don't have to take pictures, don't worry. You can distribute the presentation to everybody, no problem. So what I've given there is how people generally design with silica fume. As you can notice there, in most of the cases, the silica fume replacement level is around 7% or 10%. But when you come to ultra high performance or ultra high strength concrete, which is sometimes otherwise called reactive powder concrete, 200 megapascal concrete. Okay, this is also being produced, where water cement ratio, water binder ratio less than 0.2, 0.15 and all is used. Sometimes your binder content can exceed, and invariably it will exceed 800 kilograms per cubic meter. You'll go to 1000 also, 1000, 1200 sometimes. In that case, cement is not replaced, silica fume is added on top of the cement. Up to 25% is added on top of the cement, because there you are looking for a microstructure that is extremely dense, which has absolutely no small defects. So because of that, it attains extremely high strength. And sometimes you do also other techniques like pressurization during the setting process, which eliminates the voids internally also. So people have even experimented with 600 to 800 megapascal concrete. You make the paste so strong that it just cannot fail. And you put steel aggregate inside, so you have to actually crack the steel. Of course, all this is nice to do in the lab. In the real field, that level of strength may not really play a role. But 200 megapascal UHPC is playing a role today. People are trying to look at replacement of steel in some sections. I'm talking about structural steel in compression members, where you can easily do with UHPC. It can provide you sufficiently good flexural resistance also to provide a good performance. Okay? So again, here steel fibers are typically used, short steel fibers, but silica fume is an integral component of most of these high-grade concretes. So just to summarize, I don't know if I was expected to talk this long, but yeah, silica fume is an excellent material when designed and used with proper supervision and control. Very important to understand that. always ensure that the supervision and control with any high quality material has to be top class. It is a desirable ingredient for high performance concrete. You should use it whenever you need to do very good in durability. Of course, there are products which are also worthy to mention here, like metakaolin, which can produce equivalent durability levels to silica fume, but it needs slightly higher dosages as compared to silica fume. Ultrafine slag can also be another material that we can use, but the extent of durability, performance in terms of the test results that it gives you may not be of the level of silica fume, at least from the data that I've seen. And as I said, it's a necessary ingredient for ultra high strength concrete, without silica fume, UHSC will not be really possible. So thank you all. I'll stop with that. Questions at the end or? End, yeah, sure.
Thank you, sir, for creating the platform for today's presentation and providing a detailed understanding of silica fume. So further, we move upon to facilitate our guest of honor, Mr. Rajesh Ladhat, Managing Director, Mrs. Structural Concept Designs Private Limited, Mumbai. Mr. Rajesh Ladhat is a civil engineer, graduated from BVB College of Engineering and Technology, and he started his career as a design engineer with PT Gala Consultant Engineers, and he has worked for various projects in residential, commercial, public structures, etc. He has started his Structural Concept Designs Private Limited in 2001, and his company achieved the milestone of 1,000th project in the year 2014, and till date they have crossed more than 2,000 projects. May I now call upon Engineer Muralidharan and Mr. Siddhappa Hasbi to honor Mr. Rajesh, please. Thank you for the honor, dignitaries. Now we move upon to the major aspect of the event. I request Engineer Ravi Shankar, Executive Committee Member, ICA Chennai Center, to formally introduce the speaker, Mr. Siddhappa, and to felicitate him.
Good evening, all of you. We are happy to introduce Mr. Siddhappa Hasbi. He is a keynote speaker today. Mr. Siddhappa Hasbi is a metallurgical engineer, graduated from Karnataka Regional Engineering College, KREC Surathkal, now called NITK, Surathkal, in the year 1989. He started his career as a production engineer at Indian Metals and Ferro Alloys Limited, IMFA, in Orissa, and was associated with this company for 2 years. Since then, over the past 32 years, he has been associated with the product development and the technical marketing and the sale of silica fume, microsilica to the concrete, refractory, oil, well, and the fiber cement industries in India and other the SAARC countries. He is the managing director of an European-owned multinational company, Cornish India Private Limited, heading their business activities in India. East Asian countries, in India, and the other SAARC countries, plus the Middle East and the Southeast Asian countries. He is also working as a director since the last 4 years in the newly formed entity, Kvalitet Resources LLP. He is a regular contributor with his papers to the ACI Concrete magazine and the Concrete International UK magazine and the various construction related magazines in India. We welcome you, sir. Sir, we request Mr. Siddhappa Hasbi to come on stage.
Kannan sir, can you please join? So stage is now over to you for the presentation, sir.
Yeah. Good evening to everyone. Probably, I think in the next 60 minutes or so, I'll run through my 32, 34 years experience, starting from 1989. The topic what I've chosen is silica fume, a versatile raw material in high-performance concrete. Mineral additives or mineral admixture. What are mineral additives and mineral admixtures? They are the performance enhancers in your concrete. Polarized fly ash, PFA, ground granulated blast furnace slag, GGBS, silica fume, ricer's ash, and metakaolin, to name a few. Then normal questions. Why do we need this high performance? Why do we need these new concretes? Why do we need this high strength? And why do we need these low permeabilities in the concrete? A single answer, because we need durability. This structure is one of the North African countries. Can anyone guess the age of the structure? Less than 10 years. The ground had a lot of sulfates in it. So it's a pure sulfate attack. You can see the reinforcement. It almost looks like an external reinforcement there. The whole structure was scrapped off and it was rebuilt in 1988 to 1990. Since then, I think it's 34 years now, it's standing. Just 3-4 years, just before COVID, I think my colleague and a good friend, Mr. Robert Lewis, was there on the site. I think he said it's still standing. It's doing well. That's durability for you. Next one, what I want to show is the Kinzua Dam. I'll show the mixes and other things in detail. It was repaired 2 times. The second time when it was repaired was in 1989. It's standing. I always believe in law of 5s. Any project, it starts from the drawing board. Design, construction, initiation, propagation, damage. And I always tell people that during the construction stage itself, don't be fussy about spending a little more so that the durability will be there, because repairs are always very expensive. Coming to the product itself, what's in the name of the product? Condensed silica fume. We are condensing the silica-rich smoke which is going out of the chimney. Silica fume is a shortened version, and since it's in submicrons, many people call it microsilica. But the correct numeric rheological name is silica fume. It is not silica flour or silica dust, and it is not micronized silica. Both these products are ground crystalline quartz powders. And it is not fumed silica, it's not precipitated silica, it's not gel silica and colloidal silica. These are chemically treated silicas, but they go in for different applications, like the rubber industries and pharmaceutical industries. And coming to development of silica fume concrete, it's not a new product. It has some history. The first fumes were collected way back in 1947. And 1952, samples of silica fume concrete were buried in acidic sulfate-rich soil outside Oslo. And the durability studies are still going on. That's giving excellent results. And 1970s, filtering system and concrete trials first started in Canada. 1976, the first standard for its use in concrete came from Norway. And I've also listed some of the major silica fume concrete production startups in various countries. You see, India, 1987. The first project which used silica fume concrete in India was Deepak Fertilizers, a newly fertilizer company in the outskirts of Bombay, actually in Taloja. the concrete was just M35, but the raw materials which were used to produce these fertilizers were very reactive, very aggressive. So they wanted the concrete to sustainable. So they used silica fume there. And China started later than us, but China is multifold, many fold bigger user of silica fume concrete, mainly because two things. Locally, they produce silica fume is one thing, and their infrastructure industry is quite big as compared to the Indian industry. Currently, to summarize, there are over 12 standards and codes of practices for silica fume. ASTM C1240, I have put XX because always look for the latest one available on the stands. The latest one available now is 2020. And IS 15388, 2017. It's a second revision. And Canadian standard, and you have the European standard. It's used in the construction of world's largest project, and as per our market guesstimate, more than 10 million cubic meter of concrete is silica fume concrete every year. It's used in the construction of bridges, roads and tunnels, hydraulic structures, skyscrapers, and hazardous environment like the Deepak fertilizer thing what I for durability purpose. Standards I've tried summarizing here, the ASTM, European, Canadian, and Indian. Everything, if you see that it requires a minimum amount of amorphous silicon dioxide, 85% minimum silicon dioxide. And the next thing what I want to show is the loss on ignition and the alkalis. Loss on ignition, I think slowly, I think they're trimming it down further. It should be less than 6%. And the specific surface area, it asks for minimum 15 meters square per gram. And pozzolanic activity index, ASTM asks for 105%, and our Indian standard asks for 85%. This is one of our industry in China. Till late 90s, early 2000, this was what it looked like, highly polluted. And my marketing man tells the dollars were flying. So today, we are collecting the fumes which are going out as a pollutant. This single plant, this single industry has 18 plants, close to 150,000 tons of silica fume is produced annually. And everything, all the 18 plants are silicon metal plants. This is one of the Bhutan plant, which is producing high-grade ferrosilicon. They produce 3,000 to 5,000 tons. So generally, I think coming to metallurgically, silica fume, the production, I have tried, a visible pollution problem is eliminated by removing the silica fume from the smelting furnace, and at the same time, it's used greatly in concrete. Raw materials is quartzite and the black materials. Quartzite is crystalline silica, and black materials in various forms of carbon, coal, charcoal, wood chips, coke, semi-coke. Smelting happens around 2000 degrees. It's a two-phase reduction. SiO2 gets reduced to SiO, and SiO further gets reduced to metallic silicon. And since it's an open-top furnace, the intermittent SiO comes in contact with atmospheric oxygen, and it gets oxidized to SiO2 again, amorphous SiO2, which would have gone out as a pollutant out of the chimney. We are trapping it. We are condensing it. And running through a pre-collector, it's a metallurgically designed pre-collector pre-fan where we are segregating all the impurities by gravity separation. And silica smoke is run through the bag-house filters. This bag-house filter which is used is a reverse air cleaning system where the bags inflate and deflate. And the material of the bag is an extremely fine cotton bag. There's a company called Gore-Tex in the US. It's a Gore-Tex branded bags, and Gore-Tex guarantees their efficiency less than 5 ppm. That means all the fumes are collected. The air which is let out is cleaner than the air what we breathe, less than 5 ppm. So as collected fume is undensified in nature, where Manu sir mentioned the density starting from 180, it could be up to 250 or something that way. How should I show? 1 kg of material would be this much, or this big. So this particular material as produced is undensified. We are pneumatically densifying it to bring the density, say, between 550 to 700. Ideally, industry, depending on the dispersion and the mixing, what they ask for is in and around 600. So We densify the material for two things. One is transportation becomes very expensive. In a 20-foot container, which carries 20 tons of other raw materials, we can hardly put 7 or 8 tons of material. By densification, I think we can increase the quantity. We can come down to 18 to 20,000 tons. And also, I think while handling at the site, undensified material being lighter, it tends to fly off actually. Losses are more. So if we want, whatever we want to put in the mixer, it has to go into the mixer. So these agglomerates are loosely bound agglomerates, and they can be broken easily when we are dry mixing it. So quartzite, wood chips, and various black material. This is the front end of the furnace. What happens inside? Temperature could be between 1980 to 2010. Two-phase reduction, SiO2 getting reduced to SiO and SiO2 further this thing. Metal is tapped periodically, and some of the SiO comes in contact with atmospheric oxygen to get converted to atmospheric, rather amorphous silicon dioxide. The metal, and schematically raw materials, quartzite, black materials, carbon electrode. Carbon is also a form of carbon, and we need lots of energy. That is the reason it's not produced in India. India has very rich raw materials. We have the best quartz available, and we have black materials, but power is very expensive here. To produce 1 ton of silicon metal, we need 15,000 units of power. And to produce 1 ton of high-grade ferrosilicon, we need 10,000 units of power. So India is the only country which is exporting quartz to the countries who produce silicon metal. So when I say, show this particular chart, silica fume today is no more a byproduct, it's a co-product. We are designing the raw materials, what you call the mixed design. In metallurgical terms, I call it the burden calculation. I put the right amount of material to produce two products, the silicon metal and silica fume. And in case of ferrosilicon, it's high-grade ferrosilicon and silica fume. Silicon metal, the lumps, and the fume. How does the silica fume look like under SEM? Perfect spheres, amorphous spheres, 0.15 microns in diameter. It's finer than the cigarette smoke. Silica fume, a product of silicon alloy industry, glassy microspheres, 0.15 microns in diameter, average particle size. It's a pozzolana, it reacts with calcium hydroxide. It could be anything between 85 to 98% amorphous reactive silicon dioxide. So forms, as Manu sir said, undensified material 150 to 350. I said we densify it pneumatically to bring the density between 500 to 700. And few countries, you get the material in pelletized form also. A country like Poland, the aggregates are very reactive there. And use of silica fume in every kg of cement is compulsory there. So they get silica fume in the pelletized form, and it's interground in the cement production itself. They use the silica fume blended cement there. And the slurry, as Manu sir said, it's very common to be, its use is very common in Europe and US. It's very simple. Slurry is nothing but 50% water and 50% powder. And if I want to import into India, I'll have to pay for transportation for water, and I'll pay import duty for water also. It becomes very expensive. Only one project, Bandra Worli Sea Link, used this thing where we produce instant slurry at site, not a stable slurry. So undensified 150 to 350, densified between 500 and 700 bulk density, and slurry is 1400 kg per meter cube. The densified material, undensified material, and the slurry. Properties of silica fume, it's amorphous in nature. When I say amorphous in nature, no health hazard, no health risk. You can breathe in and breathe out. Its particle shape, smooth spherical particles, particle size, 0.15 microns. It's approximately 80 to 100 times finer than cement particle. And specific surface area, we're talking of 15,000 to 30,000 meters square per kg. What do you mean? Football, the standard football. The quantity of silica fume which can be filled in the football, that quantity can be spread over the entire football ground. It covers that much amount of area. So I've tried comparing silica fume with fly ash, slag, and OPC. It stands out to two things. It's highly siliceous as compared to the other three. And see the fineness. While the other three fall between 300 and 700, silica fume is minimum 15,000 to 25,000 meters per day. The other three are measured with Blaines, and here we use a BET, nitrogen absorption method. How do the materials look like? Silica fume on the far end there, the GGBS, OPC, fly ash. When I say it's 80 to 100 times finer, schematically how I show, this is the part of the cement grain under SCM, not a full cement grain, part of the cement grain. This will be a silica fume. It's a very, very fine material. So between two cement grains, you see hundreds and thousands of silica fume particles flooded together. Basically, physically, it acts as a filler, and chemically, it reacts with calcium hydroxide to form this calcium silicate hydride gel. This is your conventional concrete. You see that's a lot of unused calcium hydroxide and a lot of pores and cavities and things that way. Add 6 to 8% of silica fume to this concrete mix. This is what you get. It makes the concrete dense. So hydration, I've just tried putting schematically what it is. Cement, the primary hydration. Add water, the result, you get some amount of CSH to it some strength. This, I call it as cement hydration. Add some lime, add silica fume to this particular thing as a secondary hydration, this thing. Some water. The amount of CSH will go up. As a result, we get better strength in the concrete. And this, I term it as a pozzolanic reaction. So fresh concrete properties, it makes the concrete cohesive. The concrete does not segregate. It makes the concrete adhesive. There is no bleed water there, no bleeding in the concrete. All put together, it makes the concrete thixotropic. This results in improved pumping, shotcrete applications, self-compacting concrete, and it can be placed underwater. There is no washout. You can see when I say cohesive, the concrete sitting on the dumper here is quite stiff. When it hits the ground, it starts flowing. Silica fume being spherical, it gives what we call as a ball bearing effect to the concrete. Non-segregating, this a 250 mm plus clump. Two things you observe, the formwork is not all that good here. Had it been an ordinary concrete, slurry would have come down from the bottom. And also the water standing on the floor, it's not getting mixed with the concrete. Silica fume concrete does not allow anything in, nor does it allow anything to get out. It can be pumped to various distances, various heights, no segregation. Shotcrete, whatever you spray, it sticks. The rebound is minimum. See this gentleman, he is very courageous. He doesn't have any protection there. He is confident silica fume will not bounce back. Bleeding, no bleed water in silica fume. Underwater placements, you can see this environmentalist was standing there to check. He could not find any this thing in there. Placing, finishing, compacting, curing. Since silica fume concrete is produced with very, very low water binder ratio, I think curing has to be adopted immediately because surface tends to dry off. So silica fume concrete does not bleed. It must be cured properly to prevent drying out, especially in hot weather environment like ours. Mist-spraying, ponding, membrane coating, wet hessian. Common practices. Shading, minimum 7 days wet curing. So hardened concrete properties, it makes the concrete stronger, impermeable, both put together durable. And durability against abrasion erosion, against chemical attack, against water, chlorides, sulfate, and ASR, alkali silica reaction. High strength. Since last 2 years, I have changed that numbers. I used to operate 45 in India, up to 90, 100. Now, since they are producing high-grade concrete, now I've increased it to 60 to 150. We are producing really high-strength concrete today in India. Increased height designs are there in for towers for 1 mile and above. Thinner columns at floor buildings, thinner bridge decks, longer bridge spans, increased resistance to physical damage. These are the advantages what you get. And strength, if you see, I think in silica fume concrete, you are able to achieve the desired strength in the first 7 days itself, minimum 80%. And ternary blends, triple blends are the best, even better. OPC, here I've taken OPC, GGBS, silica fume. It will be a similar pattern with OPC, fly ash, and silica fume. And impermeability, you see, I think OPC and add silica fume to it, how it becomes highly impermeable. And again, the ternary blend is the best. Sulfate resistance, see, it's highly resistant to sulfate, silica fume concrete, and ternary blends. Same is the case with chlorides. It resists sulfates and chlorides, both. So, silica fume concrete typical values, in fact, what we get, by adding 6 to 10%, you will be able to achieve less than 1,000 coulombs. About 10%, I think now I would not recommend, because I think, as Manu sir said, it just acts as a filler. And since we are importing it, it's a bloody expensive filler in India. So durability specifications, as per DIN, it asks for 30, but many designers are specifying for less than 10 mm. Silica fume concrete can achieve less than 5 mm. In most of the cases, it is nil, less than 2 mm or less than 2 mm. Chlorides, they are specifying 1,000 coulombs in very aggressive environment. They are even specifying less than 750 coulombs. So these are some of the RCPT numbers what we got when we did the trials for this Tala hydraulic power project and Tehri hydraulic power project. So M30 conventional concrete, I think we are getting 2,100 coulombs. By introducing 6 to 8% silica fume for the same M30, we were something like 880 or to 900 coulombs. Ultimately, both the projects used M60 concrete actually. The coulombs read were less than 250. So silica fume based abrasion resistant concrete, I showed you about the Kinzua Dam. I'll show some slides. It was built in 1967. It came up for first repairs in 1973-75. The primary conclusion was the aggregates were not hard enough. They were soft, local aggregates. So they decided to import good aggregates from the neighborhood. And the first repair was done in 75. Come 83, 84, the whole repaired portion had eroded. Then I think this is what it was looking like. The wise heads put their heads together, did various trials. They came to a conclusion for silica fume concrete. The second repair was done in 85 to 87. It's still standing. So conclusions, do not use fiber reinforced concrete, use the lowest possible water cement ratio, use the hardest available aggregate. Continuous efforts to fight this problem led to high strength concrete containing silica fume. So what lab tests they did before coming to the silica fume concrete? Steel fiber reinforced concrete with Kinzua, that's a local aggregate, conventional concrete with soft aggregates, conventional concrete with hard aggregates, silica fume concrete with hard aggregates, and silica fume concrete with the local aggregates. It's a 72-hour testing actually. And every 12 hours they take out this sample and see the weight loss. And the weight loss has been jotted there. See, all silica fume concrete was going flat. No abrasion and erosion there. Specification, finally, what they did was, I think they wanted around more than 80 megapascals. Cement, maximum 450 kg. Silica fume, they said minimum 15%. As a salesman, I'll be very happy to sell more silica fume. And water bind ratio was 0.3. This is in 1985 in the US. This is a sample actually what they took it for testing. This is the equipment. Ultimately, what they use there, 386 kg cement, 70 kg silica fume. Water bind ratio 0.28, a slump 250 mm slump minimum. The results, 7 days 69 and 28 days they were hitting 95 megapascal, even with the local soft aggregates. After 1985, the first inspection happened only in 1998, after 13 years, 14 years. And the latest what I heard was, I think, which is still documented in 1920. They have done one more inspection. Nothing is worn out much. It's working. So placing concrete in tidal zone, I have just taken from one of the European applications. This is where the ships are parked. Because of the movement of the ship, there is heavy wear and tear. Every season they used to repair it. This was a regular practice until I think probably in 1988 to 1990. You can see how it is ruptured. They placed silica fume concrete there. You can see even after 10, 12 years, only the tampings can be seen. There's no much wear and tear. So some of the laboratory tests I'll do for Thala and this thing what we had done. This is in conjunction we did and the CSMRS in Delhi did. These are reports from both of us. The grades M30, M50, M60, M70 with 10% silica fume. Mixing is very important. I would recommend very good mixers. This is a very fine material, dispersion is a key. This mixer is really working well. Look at the mixer, if you closely look at it. So mixing sequence also, this is purely through experience. Coarse aggregates, add silica fume into the mix as early as possible, along with the aggregates, because the densified material has to disperse. It starts breaking down when it comes in contact with aggregates. Fine aggregates, some water, remaining fine aggregates, cement, superplasticizer, and water. Make sure you're adding superplasticizer when cement is in the mix, because I think we have tried also doing mixing silica fume with superplasticizer. It binds and makes a ball. It doesn't allow silica fume to disperse. So mixing sequence at site, I think we'll not be able to have the same luxury what we have in the lab. Coarse aggregates, fine aggregates, silica fume, cement, superplasticizer, water. Only recommendation is mix as much as possible. Don't be in a hurry. Give more mixing time for better dispersion. So mixes for theory, M30, M50, M60, M70, you can see. For Thala, in this case it was slag cement. With theory it was an OPC. Only changes what we made was the RPM, what recommended as per ASTM is 1100 RPM. And what we were given to understand the velocities of water encountered in any dam here is approximately 45 to 60 meters per second. Working backward, when we said with 1100 RPM, I think it was way, way slow. It was just giving us maybe 18 to 20 meters per second. So we increased the speed of this thing by 3 times. Well, all the tests what we have done in India is at 3,360 RPM to just simulate and come closer to the real life. Abrasion losses, you can see. Numbers basically are not, this thing with silica fume concrete is coming down. I'll show the condition of the samples. When we went beyond 72 hours to run this. The conventional concrete started giving away completely. Silica fume concrete was flat, no abrasion. Same with Thala. This is a 28 days cured sample before putting into testing, conventional concrete, M30. After 72 hours, this was the state. Lot of wear and tear, and the bond was not good. So aggregates were peeling off because of a weak bond. And we even collected, I think you can see from closer this thing, cracks and aggregates peeling off, you can see. We collected the residue, what was collected, the worn material. You could have seen some of the peeled aggregates because of the loose bond in a conventional concrete. With silica fume, M70, after 72 hours, only the top watery layer had gone off. The bond looks good. Have a look. And the residue, no peeling of aggregates and anything. They were holding on. So observations, use of silica fume concrete helped in reducing the loss on abrasion by around 40%. The cracks around the aggregates and conventional aggregate indicate the further dislodgement of aggregates if possible. Tests were continued. And a good bond between aggregates was seen with the silica fume concrete. And the strength alone is not the criteria. So, use of silica fume concrete helps in attaining high strength and ensures better bond between aggregates, making the concrete highly resistant to abrasion and erosion. This improved durability makes high-performance silica fume concrete the most suitable one for hydraulic structures. So terminal blends can be even better. That has been shown in Tala, in slag cement and this thing. So high-strength silica fume concrete does work as anticipated in situations of high exposure to abrasion and erosion forces. Coming to high-performance concrete in India, it's been used in construction of nuclear power projects, hydropower projects, roads, bridges and tunnels, high-rise structures, repairs and rehabilitation projects, and hazardous environment. The Deepak fertilizers, what I said. This is the one, the Preling Tower and Deepak fertilizers. This picture I had taken in 2019, done in 1990-91. It still looks new. M35 concrete. Because basically along with the aggressive raw material, they were using acid also as one of the raw material for producing. So it is basically an acid resistant concrete. Nuclear power projects. I think Kega, after that accident, they went in for the silica fume concrete dome. I think after consulting with the CEO of France. They just used 2,000 cubic meter of concrete per dome for the 2 domes. Same with Kota. They parallelly started that one in 97, 98. Based on the usefulness and what they saw, Tarapur, the new greenfield project, almost 125,000 cubic meters. The entire reactor building is done with silica fume concrete. And today, I think they're specifying for nuclear waste handling systems to prevent this radiation leakages. The requirements, the pressure containment vessel should satisfy structural integrity, leak tightness, serviceability, and durability. And high-performance silica fume concrete was able to cater all these requirements. They wanted compressive strength of 60 MPa. More than compressive strength, they wanted a split tensile strength of minimum of 3.9 or something. By doing an M60 concrete, they ended up making M60 concrete with the mean target strength of 74, 75 megapascal, and a split tensile strength they were able to hit up to 4.5 megapascals. For Tarapur, I think M60 for the reactor containment structure. Then the Calendria Award, high density concrete for radiation shielding. The aggregates were hematite ore. The density of the concrete there is 3.8 to 3.9. They use silica fume things for 2 things, no segregation and to give impermeable concrete. Within 3-4 years, there were changes. For Kega and Kota, they were using 475 kg of cement for M60. Come Tarapur, I think they were able to reduce 50 kg of cement to produce the same quality concrete. The dome. See the dense reinforcement. Did not have any honeycombing or anything. It's an operation, 220 into 2. This is Tarapur, the heavy density concreting stuff. This is a 540 megawatt plant. I think I have one of the papers in this about material, silica fume. I think it was fully dedicated to nuclear power structure. So I've taken this particular thing again. I think this was imposed in nuclear fuel handling system. See the mixes what they have used there. 232, 89, 36, roughly around 8% silica fume. And the results what they have achieved is a typical M40 leak-proof concrete. In India, they have done in Tarapur and Kalpakam, and I think others will follow. Coming to hydropower projects, we are the world leaders. A lot of silica fume concrete is used in construction of hydropower projects. Napta Jagdi, Salal, this was the first, before implementing, I think the repairs were done on this particular thing in 1991-92 on the Stilling Basin. Dulhasri, the first NHPC project, new project which used silica fume concrete. M60 concrete, you see the amount of cement what they have used there, 500 kilo cement. And today we are able to produce the same M60 concrete with 360, 380 kg cement. That's an improvement in the concrete technology. And also I think one more thing I want to show. They were not fully confident that silica fume will stop segregation. So they had added 0.5% precipitated silica also there, the first project. And with that experience, I think all subsequent projects, they removed precipitated silica. Silica fume concrete can handle it. Largi, again for shotcrete. Chimera for dams. And the flushing tunnel. Srisailam Dam, it went through major repairs, actually in 1998 to 2002. 2,500 cubic meter of concrete was placed underwater, no washout. Further, consolidated grouting was there. It was endless. They went on and went on. Kuruchu Dam, the first hydropower project in Bhutan, where silica fume concrete was used for the Stilling Basin. And come to Tala, it was a big project for us, 1,020 megawatt. The tender specified quantity for silica fume was only 73 tons in the tender. 9-10 years later, when the project was completed, they consumed more than 22,000 tons of silica fume. 28.5 kilometer tunnel, the entire tunnel was shotcreted with silica fume steel fiber shotcrete, SFRS. Typically M30 SFRS. The mixes, I think what testing what we had done, what I showed. I have just compiled all the results here. the spillway bucket. They ultimately use M60 concrete for the spillway bucket. Underground powerhouse, desilting chamber. It's a 92-meter high dam and 130 meters in length. It's in operation now. Perry, again one of our biggest projects, 2,350 megawatt hydropower plant. Again, they also ended up using close to 25,000 tons of silica fume for the construction. From the mixes, what they have used, M40, M50, and M60. Silica fume concrete has been used in all these three grades of concrete. This is the Omkareshwaran. Again, it's used in spillway. Coming to shotcrete, I'll use a few slides. Silica fume concrete shotcrete basically substantially improves the adhesion and cohesion properties of shotcrete. You are able to single spray as thick as 400 mm and above. It can be sprayed on surface with flushing water without any washout. There is a substantial decrease in the rebound using silica fume shotcrete. With OPC, we can hardly build on 60-80 mm in a single spray. With silica fume, more than 600. And look at this gentleman, he's not afraid that the concrete will fall on him. The silica fume shotcrete is standing on its own. These are the actual numbers from Mumbai-Pune Expressway. The ordinary shotcrete, it gave almost close to 60% losses, rebound losses on the overhead crown. With silica fume, we are able to bring it down to 7.5-8% SFRS. On the sides, it was almost 30%. We are able to bring it down to just 2-3%. All the 6 tunnels, Mumbai-Pune Expressway, are shotcreted with silica fume shotcrete. First one is a Barton. Once you start from Mumbai, Barton is the first tunnel. So SFRS, you can see it's in M30, shotcrete. Kamset, it's on the other side, post Lonavala, towards Pune, Kamset 1 and Kamset 2. Madap is the second one. Coming to buildings and commercial structure, a lot of contribution from Mr. Ladad on this in Bombay and surrounding areas. This in Bangalore, this Sathya Sai Super Speciality Hospital. Larsen & Toubro people have done it. They have used silica fume in the domes there. M35 concrete. Ramakrishna Mandir ferrocement shells. It's used with silica. Entire temple is done with silica fume ferrocement shells. Look at the strength, what they got, 28 days, 66 megapascals. One of the first high-rise buildings in Mumbai in mid-90s, Raheja, on the western side, Kandivali. They specified M60 for columns, residential tower. Look at the mix, 425 kg cement, 40 kg of silica fume. In 28 days, they were hitting 72 megapascals. And water burn ratio, 0.28. The Parliament Library building, again, Larsen & Toubro have done that. They have used silica fume concrete there. This was the project what I was talking, Kesar Solitaire. 3-tier basement, close to 5,000 cubic meter of self-compacting concrete, M40. I think columns for the first 14 floors were M75, and 15th onwards up to 32. It's M60 concrete. mixers for self-compacting. You can see, I think 28 days they were able to hit more than 50 megapascals, and RCPT, less than 650 coulombs. 400 kg cement, 5% silica fume, 170 kg fly ash. And for M75, 475 kg cement, 80 kg fly ash, and 50 kilos of silica fume. Mean target strength 28 days, 83 megapascals, and RCPT was less than 400 coulombs. Some of the other projects I'm just showing where they have used M40 HPC, M75 for the columns again, and M75 HPC for Oberoi constructions. I think probably more than 20 towers are done by Lasse Tubro. The columns were M75 and M60 at a later stage, at a higher stage. General Motors. This example I want to give because these people want faster construction. They wanted higher lease and development. The work started after New Year, and they wanted to complete it before monsoon. Silica fume and PC-based admixture gave them the results. In 2 days, I think basically they needed minimum 35 megapascal strength. Again, one more, IT Tower. These are all, I think, Mr. Leather's projects. Coming to roads and bridges, JJ flyover is a landmark for us. The first M75 grade concrete done in India. Again, 500 kilo cement, 501 kilo cement, and 10% silica fume. Slender sleek column, Adar Consultants. (550 kg silica fume), and see the water cement ratio, 0.29. This picture I have put crash barriers. You can see these patches, the lubricants. Silica fume concrete is not taking it in, they're standing out. This is in one of the busiest places in Mumbai, South Mumbai. Erection happened only in the night when the traffic was less. Traffic is never nil in that place. And at night, it looks spectacular. Second Narmada Bridge, again, Larsen Tubro has done it. I take this example just to compare with the first Narmada Bridge. They have done it with M60 concrete, silica fume concrete. This was done sometime, I think, 96, 97. These pictures are with a life of 20 years. Taken it sometime in 2016, 2017. Look at the first bridge. It speaks of the quality. This is the first one, and that's a new one with silica fume concrete. They use M60 for the PS, 490 and 7.5% silica fume. Delhi Metro, basically in third phase. They've used it extensively. And the new, now the fourth phase, I think they have specified for a lot of concrete of silica based on their. Again, M60 concrete there, 475 kg cement and 35 kilo cement, silica fume. And LNG project, Afghans did it in Gujarat basically, in Kutch. Basically this was for their higher lease and development. They used silica fume there. 200 kg OPC, 265 kg GGBS and 35 kilo silica fume. 0.29 water bind ratio. M55 concrete. Bandabarli, 5.6 kilometers cable stayed bridge. Eventually, I think it was 375,000 cubic meter concrete. M50 for piles and M60 grade for piers and pier caps and superstructures. The aerial view. This was the first test pile. I was on the barge when I went in the sea. I think I should give my regards to Mr. N.G. Joshi, the concrete technologist. He was the first fellow to stick his neck out and said, let's not have more than 400 kilo cement. And he was able to achieve M60 with 380 kg cement. Squared roof by the consultants initially, so that specified slurry here, 10% by weight of powder, 10% silica fume. And halfway, I think they withdrew and Dar again took up and completed the job. M50, M60, see the mixes, I think. .27, the lowest water bund ratio used there. This was the original design. This would have been nice because the central pier, it had a lift and a viewing gallery, which did not happen actually when Dar redesigned it. This is what it looks like now. These are some of the old, new projects, recent and ongoing projects. As data are being collected, photos. I have listed just a project. It's being extensively used in the Mumbai Metro Rail project, Mumbai Coastal Road projects, Bullet Train project, Pune Metro, Kanpur Metro, Patna Metro, and the Statue of Oneness in Omkareshwar by Larsen Tubro. We have supplied in Zedmo Tunnel in northeast of Srinagar, in Rohtang Pass Tunnel, and now ongoing Jojila Tunnel. Silica Fume concrete is being used. Paradise Group, I specifically want to mention 3 projects they are doing. It will be, I think, 1.2 million cubic meter concrete. 2 townships and 1 commercial, designed by Mr. Gladder. The entire 1.2 million cubic meter concrete is performance-based concrete. Second Holker Bridge in Pune, M80, self-compacting concrete for the central pier. Godbandar Road flyover project in Thane, on the Panvel elevated project in Navi Mumbai, all these are MMRDA projects. And DMRC phase 3, we have supplied to, these are the major, basically we have supplied to 10 to 12 packages there. But these 5, 6 I have taken where major concrete has happened there. Then Equinox Business Tower done by Leighton in BKC. So almost 150,000 cubic meter of M60 and M80 concrete there. And some hydropower projects I said, Puna Sangchu 1 and 2 in Bhutan, Mangdechu in Bhutan. Mintadu Liska mentioned 130,000 cubic meter. Concrete grade was not big. Water was acidic there. pH between 4.5 and 5. M30 concrete, but silica fume concrete. Milamchi water supply project in Nepal, 28 to 30 kilometers. Entire thing with silica fume shotcrete, SFRS. Now the ongoing Mumbai-Pune Expressway missing link project, which again Afcons is doing. It's an ongoing project. Delhi one project in Noida. Again, Larsen Tubro have done it. I think almost 150,000 cubic meter of M60 and M80 concrete. The Thane project has just started. Delhi Metro RRTS, Rapid Rail Transport. Mumbai-Goa Expressway, and the Polavaram Dam project in Andhra Pradesh. They've used lots of Silica Fume concrete. The list is there, but I would just tried mentioning a few. So coming to conclusion, build the structure to last. This example I have taken, I had gone during the initial stages of construction in mid-90s. Orson Bridge connecting Denmark and Sweden. Designed life for 125 years. 80 years maintenance free. The next one closer to this is Chingma Bridge. Again 100 years, 75 years maintenance free. This is a bridge connecting the new airport to the Hong Kong island. And we are not far. Bandra Worli. No durability terms have been written, but it's a wonderful concrete what they have done. Kinzua Dam, one more example for durability. And it's very common in Europe to use in thermal power stations also for cooling towers. So October 2021, again, 7 beautiful papers on Silica Fume concrete. One is mine. This is an article which we came up in Concrete International. And the HPC in hydropower projects, it all started with Kinzua as an example, and today we are the world leaders. A lot of hydropower projects have used and are using Silica Fume concrete. So HPC in India, it all started with NPC, Kega Kota, JJ Flyovers, Bandra Worli, and I can put new projects also. So advantages, use of HCC results in achieving high compressive strength, high split tensile strength, faster construction, low permeability, and for me the important thing is high durability. Build the structure to last long. Development, it's just the definition, it's a relative term. In 12 months' time, the latest development in electronics will be out of date. When I meet you the next time, I'll have a different mobile set. You'll have a different mobile set. But in 12 months' time, the latest development in concrete will still be the latest development in concrete. It's a learning process. So HPC, it's all about team effort. We all have to put our hands up together to make it possible. Thank you. Thanks for your patience here. Any questions? Okay.
Thank you so much, sir, for providing a detailed insight about the superiority of Silica Fume and with appropriate examples. So before we take up the questions, we call upon Mr. Senan Shah to share a few words to the audience. And I request upon Engineer Ravi Shankar to felicitate Mr. Senan, please. Over to you, sir.
To all the esteemed crowd that has gathered here to listen on this very, very important product, which today is helping our nation to come up with this engineering marvels, which you are all part of. As a small thing, that's a humble request. We have been trying our level best on pan-India, being a marketing and salesperson. I can just say on that part, we've been trying our level best to give the best of the product, best of the quality, best of the services to all the parts of the country. Means we have been supplying in West India, North India extensively, and with a very strong determination, we are starting our journey to towards marching towards the south of India, where the support and the thought process has been brilliant till now. With that, we again request the entire team to support us in helping give you the best product to building up the best structures of the nation. Thank you.
So, thank you, sir. So now the floor is open for the question answer session, please.
Thank you, sir, for both of you had a very good presentation. How do you compare Silica Fume with metakaolin?
Yeah. So both silica fume and metakaolin are high reactivity materials. So generally, with silica fume you get higher fineness as compared to metakaolin. So that is one difference. Of course, metakaolin has alumina, so you get the calcium aluminosilicate hydrate that again has other characteristics like chloride binding and so on. So more or less, for high performance concrete, you have to use one or the other generally.
Okay, and will there be any kind of performance difference between these two?
You can design for the same level of performance with either of them. That's what I've seen in the laboratory at least. Generally with metakaolin, you can go up to about 15%.
Okay.
With silica fume, for the same level of RCPT, you can get it within 10% usually. Yeah.
Okay. So is it mainly because of the fineness?
Yeah, generally mainly because of the fineness.
Okay.
Next question.
So, general challenge what we face is the color variation in the concrete while using this product. How can this be mitigated?
Color variation is because of what?
Because of silica film.
What in about the 3,000 kilos they are using 25, 30 kilos of silica. I don't think that will vary much.
Yes, yes.
Because the procedure itself is that, as I showed, depending on the raw materials what we add, especially the carbon, that's how the definition says it is light to dark gray sort of a thing. But will 25 kgs in a 3,000 kgs, will it make a color difference that much?
Yes.
No.
This is one challenge which we faced in one of our projects. So,
Unless you are doing especially color concrete or something that way. Because 25 kilos, 30 kilos should not make much difference in the entire 3,000 kilos per cubic meter.
yeah, not exceeding 30.
Not. But as a supplier, we try to service the project, any project, with one particular source only, so that the consistency is mentioned. So I give him a product which is dark. I'll continue to give him dark till the end. And for you, light. We'll not be changing the sources.
Thank you.
Yeah, thank you.
I have one, sir.
Yes, sir.
What is precipitated silica?
No, precipitated silica is chemically treated silica, basically. This silicon tetrachloride, which is where this chloride is bleached out and you get the silicon dioxide out. No, that's used in pharmaceutical industry and some people use in rubber industry also. Yeah, rubber industry also there. The precipitate, basically what they used, they thought that silica fume will not be able to basically segregation, control the segregation. Though as this thing they had used this precipitated silica 0.5% to be absolutely sure of non-segregation, segregation, water segregation. So later on, I think they were convinced silica fume will do the work, and they removed it from there. Only for the first project that used it, 0.5%, 0.5%.
Is that so? The cost of it. No, silica fume seems to be costlier than cement, and how it could be recommended in a bigger projects, and will it be cost effective?
No, madam, I told about the life cycle cost.
Yeah.
It works. Repairs are always expensive. And just to tell to the benefit of all the people, silica fume is not produced in India. So that's how it becomes costly. Whatever is produced here, people talk about this fine fly ash, fine GGBS and other things. The plant where it is produced is at the same rate. My transportation cost and adding custom duty to that, it makes it expensive. Otherwise, the product is not expensive at the plant. Since it's imported, it becomes expensive. With all the
So we've been traveling across the country and seeing various mixes. So we even found out in the commercial sense also that smartly using various other materials with GGBS, with fly ash, with cement, there have been comparative studies where the cost of concrete has also been kept in check. So sometimes it's like only OPC or fly ash mix in which the design mix is specifically made to attain certain strength. But then eventually, if this design mix is engineered smartly, even using silica fumes, the cost can be kept on a commercial sense alone, can also be kept in check, whereas you still get the beautiful output of the advantages of the product.
No, again, I think with respect to cost, I'll still say the same. One has to look at the long-term cost. That's what I think one slide very clearly said, 1 rupee spent today will be saving 5-10 rupees spent several years down the line. So
Recommendation goes for triple blend ternary count.
yeah, for high performance, a ternary blended system works quite well. Yes.
Any more questions?
Just to share information. Talking about testing of this silica fume. So what we found is when we use Indian standards, which says no, we can 85% is acceptable, and we have to follow the same procedure of what we use to test the fly ash. That means anything can get qualified under this 85% requirement. This is pozzolanic reactivity, yeah. So what we need to follow is ASTM. So yes, and that has to be made mandatory. I think people like Professor Manu can actually create some awareness about this requirement, because I've seen a lot of the so-called silica fume materials getting qualified because of this criterion. So yeah, that's what I want to share. Thank you.
Any more question? So if that's the case, the questions can be reserved for interaction over dinner. So now I call upon Dr. Vasuki, Treasurer, Indian Concrete Institute, Chennai Center, to formally propose the vote of thanks.
Very good evening to one and all. And on behalf of Indian Concrete Institute, Chennai Center, it's my privilege to propose the vote of thanks. First of all, I would like to thank on behalf of ICI as well as on behalf of the sponsor, Kvalitet Resources today. Our chief guest of today, Professor Manu Santhanam, sir. Thank you very much, sir. And I also would like to thank Engineer Siddhappa, who is the director of Kvalitet Resources Mumbai. And a very special thanks goes to our EC member, Ravi Shankar sir, who was the pillar in organizing this event. And I also would like to thank the entire dignitaries from Kvalitet Resources Mumbai, and also would like to thank all the participants who actively participated, spent your time, and spent in interaction. Thank you all. Thank you very much.
So thank you one and all. So the floor is open for dinner.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जनगण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Thank you everyone. I request upon the dignitaries for a group photo on the stage, please.